Let's start. Our presentation is about electrochemistry. It's a very broad topic, and I think it's one of the difficult chapters in states, and I'll try to summarize and get the most important things related to clinical biochemist. Okay, so we'll start with definition of electrochemistry. Electrochemistry involves the measurement of electrical signals, whether a current or a voltage, associated with chemical systems or chemical reactions in an electrochemical cell. Here you can see the electrochemical cell here. The electrochemical cell, you have two electrodes, and the magnitude of the voltage, there should be a chemical reaction on both sides, and as a result of the chemical reaction, a voltage or an electrical current will be generated. This signal, when detected or monitored, will be related to the concentration or the activity of the analyte of interest. Electrochemical techniques are basically potentiometry, voltammetry, amperometry, and colorimetry. The most widely used is potentiometry. And we'll start with potentiometry first of all. Potentiometric methods are based on the measurement of electrical potential or the voltage difference between two electrodes. The electrodes are called half cells. Okay, so the difference in voltage between these two electrodes is the potentiometry. So you will find two electrodes immersed in a solution in an electrochemical cell where the cell current should be zero. This is a basic electrochemical cell in potentiometry. You have two different electrodes. Both are immersed in a special solution, electrolyte solution that contains the analyte of interest. Okay, we're not talking about the patient sample. It's just a solution, a reference solution that is contained in this electrochemical cell. The maximum difference in potential between the two electrodes obtained when the cell current is zero is called the electromotive force. The potential difference between the two electrodes is usually measured with a pH meter. And I mentioned earlier that we have two different electrodes in this electrochemical cell. One is called indicator electrode, and this is one of the important electrodes that potential changes in response to the change in the concentration or the activity of the analyte of interest. While the reference electrode, the one here, is a half cell potential. It's an electrode where the half cell potential doesn't change. Okay, so the difference will be basically due to a change in the indicator electrode potential. So we have two electrodes, reference and indicator. Let's start with the reference electrodes. Reference electrodes should have the following properties. It should be easily reproducible. Should have easily reproducible potential, reversible half cell reaction, chemical stability of its component, because when the component change, especially with temperature change, these electrodes are very sensitive to temperature. So when the temperature changes, the composition might change, and that will affect the reading of the potential. So the stability is very important, and ease of fabrication and clinical use in the lab. There are three main examples of reference electrodes. The first one is not much used nowadays. It's a standard hydrogen electrode. Nobody's using it nowadays, mainly due to difficulty in synthesis while manufacturing. The common electrodes are the saturated calomel electrode and the silver chloride electrode. The calomel electrode, as you can see here, you have a mercury electrode coated with the calomel, which is what they call this, اللي هو Hg2 oxygen O2. This is one of the reference electrodes. The other common reference electrode, this is even more widely used, is the silver chloride electrode. Is basically a silver wire coated with silver chloride. Okay. The other electrodes are called the indicator electrode, and this electrode should react with the analyte of interest so that the potential reflect the activity or the concentration of this analyte in the solution. The relative response of the electrode to one species and not another species is defined as selectivity of the electrode. It's very important that these electrodes are selective. At the beginning, the electrodes were not much selective, so some modifications were applied to the older electrode to make it more specific to the analytes of interest. Nowadays, the new electrodes are very selective, and risk of interferences is limited. Indicator electrodes are basically ion selective electrodes, gas sensing electrodes, and also redox electrodes. We'll start with the commonest, which is the ion selective electrodes. This is the commonest indicator electrode used in clinical biochemistry labs, and it's based on the measurement of a potential that develops across a selective membrane. So هذه هي الidea أن you have a selective membrane. So the membrane potential are caused by the permeability of certain types of membranes. So the membrane potential are caused by the permeability of certain types of membranes to selected anions and or cations. طبعا you know that ion selective electrodes are used mainly for what? For electrolytes, basically for electrolytes, okay? The response of the electrochemical cell is based on the interaction between the membrane and the analyte that alters the potential across the membrane. The chemical composition of the membrane is designed to achieve the optimal perm selectivity toward the ion of interest. So as I said before, at the beginning, the membranes were not much selective, but now the new membranes are very selective to the analyte of interest. This slide shows basically the ion selective electrode on the left side. It's made basically of an internal reference electrode in an internal reference electrolyte. It's a solution, and you have here a selective membrane. The whole thing here is the ion selective electrode, and this is the electrochemical cell where you have the external reference electrode in the analyte solution. Now, how can we get the concentration or the activity of the analyte of interest? They apply what is called the Nernst equation, where the log relationship between the cell potential generated and the analyte activity is used as a basic for the ion selective electrode in an analytical device. There are three different types of membranes. في عندنا liquid and polymer membrane, solid state membrane, and glass membrane. All these membranes have selectivity to a particular analyte. Let's start with the first type of electrode that uses the liquid and polymer membrane. The liquid consists of water insoluble viscous solvent in which a ionophore or a neutral carrier is dissolved in that liquid. The ionophore is the hydrophobic organic ion exchanger that binds specifically to the analyte of interest, the analyte that you want to measure the concentration of it. That liquid is soaked in a thin solid membrane, such as cellulose acetate, to make up the whole electrode. Now, the commonest ionophore used is the one for potassium, and I'll show you in the next slide. But nowadays, different ionophores were developed to measure different analytes. This slide shows the classical potassium electrode, the potassium electrode that is used for measuring potassium in serum in most of the labs here in Kuwait. And it has, as you can see here, again, this is the internal reference electrode. Here you have the internal reference solution. And here you have the selective membrane. The selective membrane for potassium uses an antibiotic called valinomycin. This is the valinomycin. These circles are the valinomycin. So what happens here, when you apply this electrode to the serum, the patient's serum, the potassium crosses the protective membrane here, and it will be taken by the ionophore, which are the neutral carriers. So only the potassium will be taken by these ionophores, okay? And then that results in a change in potential. The difference in potential measured is related to the concentration of potassium present in the patient sample. On the other hand, the solid state membrane electrodes uses single crystal or pressed pellets of salt of the ion of interest. And the last membrane electrode is the glass membrane electrode. That was the first and the most widely used ion selective electrode, and it's used for pH measurement. The electrode consists of a glass or plastic tube with a thin pH sensitive glass membrane sealed in a tip. The bulb contains an internal solution. Now, the internal reference solution is basically HCl, into which the silver wire coated with silver chloride provide the internal reference standard for the pH measurement. I'll show you the pH electrode. Now, what we're talking about is basically this one in the dark blue. Okay, so this is the glass membrane electrode, not the whole thing. Okay, so the glass membrane is made membrane electrode is made of internal um, um, reference electrode, which is silver chloride. The solution used is HCl, and here you have a thin pH glass membrane. So the pH electrode is very important to be soaked in water all time to dissolve the glass and to start the reaction. Okay. So what make the glass membranes electrode more selective or sensitive to hydrogen is the composition of a glass itself. The glass made in pH meters is basically made of silicon oxide, sodium oxide, and calcium oxide. So what happens here is basically most important is the sodium, okay? If you place this glass electrode or pH meter in an acidic solution, acidic solution has a lot of proton, a lot of hydrogen. So there will be an exchange for hydrogen with sodium. So the proton from the solution will be taken up into the glass membrane and the sodium will be exchanged out. So this exchange will result in a change in potential, and this is how the pH is measured, okay? And the opposite is true in alkaline solution. The exchange will be in the opposite direction. The proton will get out and the sodium will get in, and that will result also in a change in potential that is, when measured, will result in, will give the value of the concentration or the activity of the hydrogen ions. Uh, Different glass membranes were developed, not just for hydrogen. Nowadays, also sodium is measured by glass membrane electrodes. Okay, I want you to check. أغلب المستشفيات are using AU, صح? So I want you to check what is the type of electrode used to measure sodium. It is, but what is the type of electrode? Okay, so let's share ما توقع أحد عنده DXC, all of us عندهم المفروض AU. Okay, so let's share the second type of indicator electrodes. خلصنا من ion selective electrodes. Now we start with the gas sensing electrodes. The commonest gas sensing electrode is the one used to measure the partial pressure of CO2. It's called the CO2 electrode. It has an outer membrane that is very thin and selectively permeable to CO2. On the opposite side of this selective membrane, you have a thin electrolyte layer consisting of a weak bicarb salt and chloride salt. The pH electrode, اللي هو hydrogen ion selective membrane, and silver chloride reference electrode are in contact with this solution, the weak bicarb solution. The CO2 electrode is self-contained potentiometric cell. That means that it has the two electrodes in the same cell. The carbon dioxide gas from the sample diffuses through the membrane and dissolves in the solution, the electrolyte solution. And this reaction will take place. The CO2 react with the water to form the carbonic acid. Carbonic acid dissociate to give you the bicarb and the hydrogen. Now, the relationship between the sample CO2, partial pressure of CO2, and the signal generated by the internal pH electrode is logarithmic and is governed by the Nernst equation. So the H generated is directly related to the concentration or the partial pressure of CO2. Is that clear? Now, this graph shows what we mentioned earlier. This is a classical picture of the CO2 sensor. Here you have the one in red is the thin permeable membrane for CO2. And here you have the hydrogen or the pH meter, the whole thing here. This is its internal reference electrode. This is the solution. And here you have the glass membrane of the hydrogen electrode. So this is one electrode, and this is your reference electrode of the CO2 sensor. Okay, so what happens again is that when you apply the sample, the patient sample here, then the CO2 diffuses, only the CO2 diffuses through this selectively permeable membrane, and the CO2 react in this space with the electrolyte solution, and there will be a change in hydrogen concentration. This change will be sensed by the hydrogen or the pH electrode. Okay. Ion selective electrodes used in clinical chemistry. المفروض هذا يكون قبل. اوكي احنا الغاز يكون بعده. الاين selective electrodes in chemical عندنا glass قلنا with solid state liquid polymer. Some also include gas sensor as part of ion selective electrode في بعض textbooks. So what is the common use of glass? Mainly the pH meter for measurement of hydrogen and also sodium. Okay, solid state is basically for chloride, liquid and polymer mainly for potassium, but it can also be used for other electrolytes. Ionized calcium. Where can we measure the ionized calcium in biochemistry lab? In which analyzer? In blood gas analyzer. In blood gas analyzer. What we measure in بالAU is different. It's not ion selective electrode. Okay. Actually, I need to check that out, but usually we use different methods. The ionized, which is the more useful and sensitive test for calcium level, is the ionized calcium. And the best way to measure it is by using the blood gas analyzer. And then a gas sensor, we mentioned the one for CO2 and also for ammonia. Now we'll move to the third type of indicator electrode, which is the redox electrode. It's basically, the basic principle is that any substance that takes or accepts electron is called an oxidant. And any substance that donates or gives electron is called reductant. So redox electrode, in an electrochemical cell, the electron may be accepted from or donated to an inert metallic conductor, usually platinum. Reduction process tends to charge the electrode positively by removing the electron, and an oxidation process tends to charge the electrode negatively when they add the electrode. So you will have one positive and one negative electrode. So then the electrode potential for a redox couple is defined as the couple's potential measured with respect of the standard hydrogen electron, which is set equal to 0. Anyway, we'll just skip this one. An example of redox electrode is the hydrogen electrode used in pH measurement. Another example is the silver chloride electrode. This is the most widely used redox electrode. It's very stable electrode. Also the calomel electrode. Do you remember where we mentioned the calomel with silver chloride? When cano? Reference, yes. So these are basically based on a redox coupled reaction. Okay. Now, since we're talking about the ion selective electrode, I think it's important to mention about the direct and indirect potentiometry. Now, the older analytical methods like flame photometry, which is not used anymore, يعني أنا ما لحقت على flame photometry. الانdirect ion selective electrode, the flame photometry and indirect ion selective electrode, they measure the electrolyte by measuring the concentration in millimole per liter. Okay, this is the way we measure the electrolytes. Sodium, potassium, كلها millimole per liter. Molality is something different. It's not the molar concentration. The molality is the measure of the moles of ion per mass of the solvent. وعادة الsolvent شنو? Water. So the molality is the millimole per kg solvent. طيب, how these two are related, the concentration والmolality. Let's take an example of sodium. The concentration of sodium in millimole per liter equals the molality of sodium, which is ال okay, multiplied by the mass concentration of water. The mass concentration of water is in kilogram per liter, and the molality is millimole per kg. So kg will be cancelled, right? Kilogram in numerator with denominator, then you will end with the concentration unit of millimole per liter. So this equation shows how the molality and the concentrations are related. So the factor that affect whether these are close, well, values are far from each other, is the mass concentration of water. Okay, now normal plasma, the mass concentration of water is approximately 0.93 kilogram per liter. But in some specimens لما يكون البيشنت لايبيميك بالذات إذا كان triglyceride أو إذا كان عند البيشنت hyperproteinemia مثل في الميلوما, multiple myeloma, has a lot of paraproteins. So when the proteins and lipids are present in excess, these are the main constituents of the solid fraction of plasma. Plasma is made of what? Water fraction, and this is the major fraction, تقريبا 93%, and only 7% is made of solid components اللي هو basically طبعا blood cells نفسها, وعندنا الليبيد والبروتين. Now when the lipid proteins present in excess, this factor will be affected, which is the exactly. فthis will make a greater change between اللي هو concentration millimole per liter and the molality of the analyte. Okay. Now, a significant advantage of direct potentiometry now اللي تكلمنا عنه كان basically مع الفليم photometry ومع indirect ion selective electrode that uses a dilution. Now, direct potentiometry by ion selective electrode for the measurement of electrolyte is sensitive to molality and therefore is not affected by variation in concentration of protein or lipids in plasma. Methods that use a dilution مثل flame photometry وال indirect ion selective electrode, what we do usually is احنا ما نسحب الدم كله, احنا we take only few milliliter من the patient, صح? So when you draw the blood, you centrifuge, you separate اللي هو blood cells كلها, you end up only with the plasma or حتى serum. You have now تقريبا 7% المفروض protein, والريميني راح يكون الwater. Where do we measure electrolytes? In the water fraction. طيب. Now, in these methods, only the water phase of the sample is diluted. احنا we apply dilution. المشكلة كلها بالdilution. When we do the dilution, the concentration of the analyte of interest in the water fraction will be falsely low. Okay, so in these methods we don't look at the blood as a whole, we look only for the water fraction. So there's a risk of what is called pseudohyponatremia, and I'll show you this graph. Now this is the normal serum, the one on the left, okay, where you have 7% solid and 93% water, and the dots that you have here, let's imagine in هذيلا هم sodium. Now when you do the dilution, the dots will not look يعني ما في the reduction in the number of dots or sodium, so it will be okay, nothing will be changed. The sodium here will be equal to the sodium there. لكن the problem when you have high protein or lipids, your water fraction in the sample that you collect is less. Okay, and then because this one is less, when you dilute, the reduction of in sodium will be even magnified, will be more, and it will be more prominent. This is called the electrolyte exclusion effect or the pseudohyponatremia. And the best way to know if the patient is having a true hyponatremia ولا pseudohyponatremia is to measure one single biochemical analyte. شنو هو؟ No. Direct. Okay, بس في something you don't have direct in all labs, صح؟ بس عندك something very يمكن total protein, yes, it can very high, it can give you a hint. TG, okay. Osmolality. اوكي. اي بيشنت عنده هايبونيتريميا عاده يكون الاوسمولاريتي لو، لكن في السودو هايبونيتريميا الصوديوم is very low لكن الاوسمولاريتي is normal. So this might give you a hint to or يعني will guide you to the diagnosis. Now, regarding the electrodes that we mentioned, special care should be applied to these electrodes because these electrodes are made from fragile and sensitive material. Care must be taken to prevent breakage and to maintain the tip in moist environment. So some manufacturers provide a protective covering for these electrodes. And it's very important to follow the instructions from the manufacturer for handling and storage of these and the cleaning of course of these electrodes. عادة الالكترودز يمكن تشوفون المخازن بالمختبرات، عادة الريجنتس كلها موجودة إلا الالكترود. عادة ينحط بمكان سبيشل حق مهندس الجهاز، أو إن عندنا سينيور من سناير المختبر يكون حاط له الالكترود separate. Okay, so because they need special handling and حتى الانستولمنت يحتاج someone يعني عارف الموضوع. طيب ننتقل على another electrochemistry method which is the voltammetry or amperometry. Now in contrast to potentiometry, voltammetric and amperometric methods are based on electrolytic electrochemical cells in which an external voltage is applied. So we're not measuring now the voltage. An external voltage is applied to the electrochemical cell, to a working electrode, and the resulting current, an electrical current will be will result. Now the current that is generated when monitored will be proportional to the concentration or the activity of the analyte of interest. Okay, so في potentiometry we measure the voltage. الvoltammetry والamperometry we measure the current. Okay, what's the difference between voltammetry and amperometry? الvoltammetry البوتنشال voltage applied is not the same, can't change, while in amperometry the voltage applied is always fixed. Okay, but both you need to measure the current to related to the concentration of analyte of interest. طبعا they consider amperometry more sensitive than the voltammetry because the background noise is less like any other method يعني. Now الامبيرومتريك sensors هذا البوتنشال amperometric sensors there are different types. في عندنا oxygen electrode, glucose electrode, and it can also be linked with the liquid chromatography as a detector. Okay, and I'll show you inshallah in the next slide. Let's start with the oxygen electrode. The oxygen electrode is basically used to measure the oxygen saturation. Okay, so شنو البرنسبل مالته؟ هو basically you have here a selective membrane for الأكسجين. Okay, and you have two basic electrodes. This electrode is a platinum electrode. It's the working electrode, while those at the sides are the silver chloride reference electrodes. So what happens now when you apply the patient sample مثلا هني, the oxygen will permeate through the membrane and it will react at the platinum working electrode. It will get reduced. When the oxygen is reduced, there will be a current generated, and that will result in this will be calculated to give the concentration or the partial pressure of oxygen. So this is the principle of Clark style amperometric oxygen sensor. Glucose, by the way, in the past, the oxygen sensor was used only for oxygen, but currently it's also used to measure other analytes. في AU, this one is used to measure another analyte. Can anyone tell me which analyte? No, في AU. It can be used to measure glucose, yes. It can also be used, I'm not sure for AU. It can also use for uric acid, lactic acid, for glucose. When you apply an oxidase enzyme, مثلا glucose oxidase enzyme, شو اللي راح يصير؟ راح يصير في consumption of oxygen. فهني I'll show you الحين في الجلوكوز. Glucose by sensor is commonly used, and what happens here إن إحنا we apply an enzyme with the sensor, with the electrode there is an enzyme, and that is called the biosensor. because there is an enzyme incorporated with it. The enzyme in this glucose biosensor is basically oxidase, glucose oxidase. So when glucose react with oxygen by the action of in presence of a glucose oxidase, you will have a gluconic acid and hydrogen peroxide. Okay, so the oxygen is consumed, صح? Now the hydrogen peroxide generated will react at the working electrode that you have here, the platinum electrode. This reaction will result in an electric current that when monitored is directly proportional to the glucose concentration. Okay, now this glucose biosensors are used widely, can be used in a glucometers, في الباتشز اللي ينحط على البيشنتس arms to monitor glucose. So these are the applications of amperometry for glucose monitoring. And lastly, amperometry and even voltammetry can be used as a detector in conjunction with liquid chromatography. With liquid chromatography, the samples will be, the analytes will, after elution from the column, can be directed to special electrodes. And reaction with these electrodes can result in generation of a current, electrical current, that is directly proportional to the concentration of the analyte of interest. There are many different analytes that can be measured by liquid chromatography, electrochemistry detectors, homocysteine, therapeutic drugs, anti-epileptics, some antibiotics, amoxicillin. Many different analytes can be measured by this method. Catecholamines can also be measured by this method. في one more يمكن I missed the slide اللي هو colorimetry is the last example of electrochemical cell. The basic principle is that you titrate the sample, okay? So you apply a constant current and you titrate the sample, and the time spent for titration is related to the concentration of analyte of interest, okay? Let's focus mainly على potentiometry, and أهم الامperometry is also important, okay? Now, before we end this presentation, it's very important that when you finish reading any chapter and methodology, يعني, after understanding the principle of the method, it's very important to know the pros and cons of using this particular method. Because if you want to establish a new lab, you want to know, يعني مثلا, sodium can be measured by many different methods. Why should I use an ion selective electrode and not atomic absorption? صح? I can use the atomic absorption for electrolytes. So why should I use ion selective and not atomic absorption? So it's very important to try to find out the advantages and disadvantages of using of all the methods that you're supposed to study. بعضهم يمكن you can find it في tests, في بعضهم لا, with experience you will know it. Now, ion selective electrodes ولا حتى potentiometry electrochemistry in general. What do you think the advantages of using these methods? شلون ذلك؟
Not very expensive.
Exactly, it's not very expensive. هو in fact الالكترود الواحد is not cheap ترى. بس the good thing is that الالكترود الواحد once you load it بالجهاز can stay for 3 months تقريبا أو 2 months على حسب اللود. Okay, so لما نطالع ال overall cost لا راح يكون أوفر لي من شغلة ثانية. The cost, yes. Ease of what?
Easy of using it.
شلون صار easy؟ لأنه automated. It's not manual. I can adapt it في automated analyzers. Yes. بعد.
ما يتأثر على حسب في واحد يتأثر.
Sensitive. Yes, it's sensitive. طبعا especially the current electrodes are very sensitive and selective. Okay. Sensitive يعني شنو؟ what's the difference between sensitive و selective?
For the low specific concentration.
Exactly.
For the local.
It's a detection. It can detect the sample even when present in small concentration. Yeah, it's very selective. This is also another advantage. Does it need a large blood sample? لا, عادة small volume to be measured. So these are the common advantages, or مو common. These are the advantages of electrochemistry. Disadvantages?
Rapid.
شنو؟
disadvantage
إيه؟
ممكن مثل ما قلنا يتأثر مع الهايبرليبيديميا
temperature fragile ينكسر لازم أحفظه بمكان معين. في very common disadvantage which is protein coating.
contamination.
انه هو لا بروتين كوتينج في انترفيرنسز ممكن contamination. خلينا نقول الانترفيرنسز يس قد يكون في انترفيرنسز بس with the current electrodes these interferences are minimized. لكن في مشكلة اللي هو البروتين كوتينج. البروتين in the samples can deposit on the electrode فprevent الرياكشن. اوكي سو كان يعني اذكر خلينا نقول المهندس يجي يقول طلع الالكترود ونقص له. اوكي في بعض الالكترودز has a special protective membrane that prevent the deposition of protein on the electrodes. This fragile قلنا this is the common شو اسمه disadvantage of electrochemistry.
interference اللي هو اللي إذا كان
في interferences but now is less. Okay. I think we reached the end of electrochemistry. Do you have any question?
دكتور بس البروتين كوتينج عادة أنا قال إنه يكون contamination
No البروب شيء. البروب هو the loader اللي هو اللي يعطيك يسحب. اوكي يسحب من السامبل يسحب من الرياجنتس الموجوده. لا البروتين في السامبل نفسه. انت الحين when you put the electrode نحطه في شنو؟ patient sample. patient sample فيه بروتين صح؟ فالبروتين تلصق على الالكترود فلما coat the electrode الالكترود ما راح يشتغل كأنه عليه صار كفر. اوكي so they need to wash it every now and then. so yeah فشي يكون خالصين. يلا يعطيك العافية